After studying the operation principles of solar cells and different types of technologies, in PV3X the PV systems have been studied. In PV3X we considered a variety of PV system related topics like location issues, the operation of PV modules, the balance of system components and the financial aspects of PV systems. In the next few videos we would like to remind you of all the content covered in the PV3X photovoltaic systems course. If some topics seem unfamiliar, we encourage you to return to the PV3X course and revisit those topics before attempting the practice or proctored exam. Let's begin by discussing the location issues. To calculate the irradiance received by a solar module at a specific time instant, first we need to determine the position of the sun from the perspective of an observer at a given location on the Earth. Using a simple algorithm, we can calculate the solar altitude and azimuth at a specified instant in time, knowing only the latitude and longitude of the observer. The irradiance received on the Earth's surface can be measured using a pyranometer. If the pyranometer is placed horizontally, we can measure the global horizontal irradiance. Global horizontal irradiance has two components, the diffuse and direct irradiance. The diffuse horizontal irradiance can be measured using a horizontal pyranometer including a shading element that continuously blocks the sun disk. The direct normal irradiance can be measured using a pyrheliometer, which is continuously pointing to the sun. Remember that to calculate the direct horizontal irradiance, we must take into account the effect of the solar zenith angle. The irradiance received by the surface of a PV module, usually referred to as the plane of array irradiance, can be determined using the irradiance measurements and a transposition model. The plane of array irradiance has three components. The direct component is calculated with the direct normal incidence, DNI, and the angle of incidence of the sunlight of the module's surface. The diffuse component is calculated with diffuse horizontal irradiance, DHI, and the sky view factor. Finally, the albedo or reflectant component is calculated with the global horizontal irradiance, GHI, and the sky view factor. Both the angle of incidence and the sky view factor can be determined with closed formulas that depend on the module orientation. By integrating the results of irradiance calculations throughout an entire year, we can obtain the annual irradiation on the PV module. The calculation of annual irradiation can be performed for different combinations of module tilt and azimuth angles to find what are the best tilt and orientation of a PV module in a specific location. In this graph, we show the annual irradiation as a function of module azimuth and tilt in a free horizon location in Delft in the Netherlands. Buildings, trees and other objects around the PV module affect the solar irradiation incident on the module's surface. Therefore, when the horizon at the location of the PV module is not free, a landscape survey must be carried out. The landscape survey can be carried out on site with a camera or remotely using LiDAR data and computer-aided design models. The resulting skyline profile can be used to determine the effect on the different irradiance components. The direct irradiance component on the plane of array becomes zero when the sun is blocked by the skyline. This effect can be taken into account using a binary function called the shading factor. A raised horizon also affects the sky view factor, which is used in the calculation of the diffuse and the albedo irradiance components. When the horizon is not free, the sky view factor cannot be calculated with a closed formula, but it can be obtained using computer-aided design software packages. When the geometry of the module and the landscape becomes more complex, it's possible to use more complex irradiance calculation models. The model discussed in the second week of the course uses a sensitivity map generated with ray tracing simulations and sky maps to calculate the irradiance distribution on the surface of the PV module. Once the irradiance on the surface of a PV module is known, the electrical power generated by the module can be calculated. The voltage and current generated by a solar panel depend on how the solar cells are connected. When cells are connected in series, the voltage of the solar cells add up. On the other hand, when cells are connected in parallel, the current of the solar cells add up. In most commercially available crystalline silicon PV modules, all cells are connected in series. Under uniform illumination conditions, the IV curve of the module looks like the one shown in this plot. If one of the cells in the array is shaded, the current of the module is limited by the shaded cell and drastically reduced. In order to circumvent this problem, bypass diodes can be added in parallel to each cell or a group of cells. If a cell is shaded, the bypass diode will offer an alternative path for the excess current to flow, preventing damage in the shaded cell and allowing the module to generate a higher amount of electric power. When solar cells are exposed to a higher irradiance level, the output current and voltage of the module increase. However, not only the irradiance has an effect on the output characteristics of a solar panel. When the temperature of a solar module increases, the voltage of the module decreases and the current slightly increases. Overall, temperature has a negative effect which reduces the output power of a PV module. Both temperature and irradiance effects can be combined to determine the operative efficiency of a solar cell. Therefore, it's important to determine the operative efficiency of a solar panel. In week 4, we have discussed the effects of temperature on the external parameters of a solar module, and we also presented different models to calculate the operative temperature of a solar panel. Most of these models are empirical, but we also looked into models based on the thermal balance of a PV module, which takes into account the incident irradiance on the module, the convective heat transfer, and the radiated heat transfer. This model can be solved using an iterative process. Other practical aspects analyzed in week 4 are the row spacing and the shade-free time window of a PV array. Using the analemma diagram at the certain location, we can obtain the relevant angles to calculate the row spacing needed to avoid mutual shading in the desired time period. This concludes the first part of the PV3X summary video. In the next part, we will continue with the balance of systems.